today?
Totally awesome, sir.
All right, today we're going to be working on lesson 6. And the question is, how can the acceleration and tension be calculated for two masses connected by a string when there's no friction force? And then in a future lesson, we're going to come back and add in the friction force. Now, just by writing down this question, you're probably not really sure, what the heck you're talking about. So I want to draw two diagrams, one with a more real-life scenario and then more with a textbook look to it. So here we go. Divide this in half here. And here we have a picture of a table. It's a very smooth table. And if the problem ever says it's a smooth table, you know that basically you can neglect friction. And on this smooth table, there is a tablecloth draped over. And on top of the tablecloth, there's a fishbowl. Tablecloth, one word?
No.
Compound word.
Or two words? Tablecloth?
Sure.
I think it's one word.
I think it's one word, yeah.
One of those things that are
Nobody cares about that though.
In the fishbowl, of course, there is water. And then there's
fishy.
and
That's amazing actually.
there's this big overweight cat that wants to get the fish. But this cat can't jump up on top of the table. So it's got a plan. The plan is for the cat to jump up and grab on to the tablecloth with its claws.
That's beautiful.
Smart guy.
Dude, that's actually very well done. Let's give him a round of applause.
That is amazing.
And the cat's gonna pull the tablecloth and drag the bowl over till the whole thing comes around.
Cat.
How many people here have cats?
Yup. They smell.
Not one person?
She hates all animals.
Do you a dog? I like cat person.
I like cats, but I'm allergic to them. You know, they bother my allergies.
Do you a dog?
Stinks.
I have a dog.
You're a dog person, right?
I'm a dog person. All right. So, ladies and gentlemen, this is like the real scenario, but frequently this problem is shown more textbook stylish like this. So, here's a new look for the same exact problem. Here's the table.
Yeah, honestly, like you should do my art homework.
Fishbowl. I'm impressed by the fish.
Honestly, you're just amazing.
And then the fishbowl is just represented by a mass. Call it M1. And mass of the fishbowl, and I don't know, say that fishbowl,
20.
let's say it's 10 kilograms.
I would say 20 kilograms.
And then, instead of having a tablecloth draped over, imagine that there's like a pulley, a ball on a wheel, or a wheel on a little axle there, a pulley. And then there's a string draped over the pulley, connecting mass to another mass over here, which represents the fat cat. M2. And, let's say that that's
50.
15 kilograms. And typically what you have to solve for is how fast the cat is going to be accelerating downward, which is exactly equal in magnitude to how fast the fishbowl is going to be accelerating to the right. Because since the tablecloth is like connecting the two together, if the cat is accelerating downward at a certain rate, the fishbowl is going to be accelerating to the right at the same exact rate. So on this diagram over here, we're trying to find out how fast is M2 accelerating downward, which is exactly equal in magnitude to how fast the mass up here is accelerating to the right. So one of our questions is, what is this acceleration? And then the other thing we're usually asked to find is the tension in the tablecloth, which is compared to the tension in the string. So when this cat pulls on the tablecloth is going to be pulling the bowl over, so there's going to be a certain tension in that tablecloth. That same tension is going to be holding the cat up. It's the same cloth connected. Likewise over here, however much the rope is pulling on the object to the right, the tension in the rope there, that's going to be the same that the tension in the rope is over here, holding the mass up. So the other question is, what's the tension in the rope, which represents the tablecloth? So this is a two-mass problem where the two masses are connected by a string. We want to know the acceleration of each of the masses, which is going to be the same value because they're connected by a string. And the tension in the string. Now, job number one, the plan, Stan. One, we're going to draw a free body diagram for each of the masses. And it's very common to draw that free body diagram right on the original diagram. Remember, a free body body diagram shows all the forces acting on each object. So we're going to draw a free body diagram for each mass. I'm going to make some room over here.
Wait, you forgot the T.
Oh, you could have just made more room. You can extend the table.
Okay. Okay. So sometimes the object is freed up from the rest of the diagram. So I could take this M1 and I could pick it up and redraw it over here and label it like M1, like that, yes?
Yeah.
Okay, but sometimes people don't redraw the free body diagram over here, they just draw it right on the original diagram.
Okay.
So it's kind of like your choice,
That makes sense.
but nonetheless, I'm going to do it both ways. So if this here is M1, which represents this box over here, we want to now draw all the forces acting on it. Well, what are the forces acting on it? I mean, I labeled one of them already. We have that tension force, which is the string pulling the object to the right, like that. So I could draw that over here on this one as well. The string is pulling the object to the right. That's the tension force. What other force, Nicole?
Isn't there like a normal force keeping it on the table pushing?
Right. The table below is pushing it up like that. But normally people don't draw it that way, even though that's where it is. It's underneath, pushing up, the normal force. But it's usually drawn like this, up like that. So that's the normal force. The table below, holding it up. And I could draw it over here too if I chose to do my free body diagram over here. Thomas, what other force is acting on that M1? Come on, come on.
It's being pulled down by gravity.
Exactly. The force due to gravity, also known as the object's weight, is pulling it down. So its own weight force is pulling it down. Now, instead of labeling that F sub G, what's a very common practice is to remember the fact that the weight force, F sub G, is equal to the mass of the object times the acceleration due to gravity. So instead of labeling that F sub G, the weight force, the cool thing to do, all the cool kids are doing it, is to label it mg instead. And since this is m1, instead of labeling this F sub G like that, the weight force pulling it down, it's very common to label it
M1G.
M1G. M1 times G is just the weight force. So we have,
So that's like the same thing as saying like mg.
exactly, the exact same thing as saying FG. Now in the future, the table might not be smooth, and there might be a friction force. So if this object is going to be moving to the right, this way here, but if there really was a rubbing force underneath the bottom right here, which way would the friction force be acting, Richie? To the left. So we're not going to add it into this problem, but you know, in the future we'll have a friction force going to the left, like that, and a friction force going over here to the left like that.
Draw that.
No, don't draw it here because there is no friction force here because they said it was a smooth table. So that's all we have there on M1. Now, let's take a look at M2, shall we? M2, I'm going to free it up from the rest of the diagram. M2. And what forces are acting on it? Well, look, I have one drawn already. That tension force in the string, that same string, which has the same tension throughout the whole string, is holding it back. So whatever this tension is, it's the same exact tension here. So I draw it like the same length. Tension force. But there's one other force. TJ, what other force is acting on?
Gravity.
The force due to gravity. But instead of calling it F sub G, like right here, no.
You can do M2G.
M2G, exactly. So instead of calling that FG, I could just call that M2G because of this. So, and I know that it's going to be bigger than the tension force because the fat cat's going to be pulling the whole thing down. So I know to make that a little bit bigger than the tension force. So again, that's FG of the cat, or M2, but instead of calling it FG, I just jump right to the chase. All the cool kids do it. M2 times G.
And is that the same thing as the tension force? Would that be the same force?
Force of gravity.
If the object was at rest, or if the object was moving uniformly, then they would be equal.
Got it.
But since we kind of already established in the problem that it's going to be accelerating downward, we know from law number 2 from a man named Newton that if it's accelerating downward, then there has to be an overall net force downward. So this downward force has to be bigger than the tension force upward.
Got it.
Right?
Thank you.
I don't get why it's M. Like, I get F of G equals mg, but why M?
G equals.
M times G? But why is it M, not just like G or something else? Just like the question with the variables.
Well, G is the acceleration due to gravity, which is in meters per second squared. This is the force due to gravity, which is in newtons. So they're not equal to each other. They're related to each other, and the proportionality constant is the mass. Okay? That formula is a direct descendant of law number 2, which says that the net force equals the mass times the acceleration. And remember, when we use that formula, it's like we dream in our mind that we're picking up the object and allowing it to free fall. And if it was free falling, then what would the acceleration be? 10 meters per second squared. And the overall force acting on it would just be the object's weight force, S sub G. Okay, so here we have our free body diagrams. Here's for M1, here's for M2, and like I said, a lot of times people do the free body diagram right on the original diagram. So, check, we have number 1 done.
There it is.
Okay, number 2,
How many steps are there?
3. It's as easy as 1, 2, 3.
Oh, look at that.
It's not that.
Those are
It's not that.
Which is step 1 is like
Step 1 is long.
A, B, C, D, E, F.
Step 2, we're going to apply law number 2 from a man named Newton. So apply F net equals M times A to each mass. And when we do that, we have to make it crystal clear which way is the positive direction. And it's arbitrary. You get a choice. So I'm going to put in parentheses here. Choose positive direction for each mass.
Do you want to keep it the same positive direction?
Not necessarily. Not necessarily. For example, are we ready to go back? Whoa, too far.
I don't really understand the whole parentheses.
All right. Well, you see this object right here?
Yes,
Which way is it going to be moving?
to the right.
To the right.
Yeah.
So we want to make to the right the positive direction.
Okay.
If it was moving to the left, even though normally to the left is a negative direction,
You would say the left is positive.
we would say the left is the positive direction. So we want to make whichever way the object is moving the positive direction. So it's very common just to say for this upward object here, hey, we're going to make this direction here the positive direction.
Okay.
And then over here, this other object
You're moving down.
is moving down. So we want its acceleration to be positive. Now it's very common that down is the negative direction, but we don't want to make it the negative direction here. So basically, since this object is going to be moving down, we just say, hey, look everybody, in this problem, we're letting down be the positive direction.
Gotcha.
So now when we figure out this acceleration right here, is it going to come out positive or negative? Positive. And when we figure out this acceleration right here, is it going to come out positive or negative? Positive. And since they're connected by the same rope, and they're both positive, they're going to be the exact same A. And ultimately, we're going to have two equations with two unknowns. And when you have two equations with two unknowns, you have to have the same two unknowns in both equations. So you need the same A here as you do here. So we don't want one to be positive and one to be negative. So we always set it up so that both of them are going to be positive.
Isn't that A just like gravity?
No, no, no. If we cut this string right here, cha-ching, I cut the string, then it would be falling with the only force acting on it is its own weight force.
The tension from the rope is like.
But the tension from the rope is slowing it down. It's like that object right now not only is pulling down itself, but it's also dragging along all this extra mass, all this extra inertia, all this extra sluggishness. So it's going to be less than G overall. All right, so what I think I'm going to do now is get rid of this picture over here. Actually, I think I'm going to get rid of this again. Okay, so F net equals M1 times A. Now again, don't draw this, but let's say there was a rubbing force here, right here, and let's say there's a force of friction, like that. If there was a rubbing force right there, and now we have the rope pulling to the right, and we have the friction force holding it back, if there was both forces, but we know the tension to the right is going to win the little tug of war right there, what would be an expression for our net force right here? What would be the thing we substitute? Remember, the net force is like the resultant force. So if they're in the opposite direction, what can I say, Zach, for an expression for that net force right there in terms of these forces right here, these horizontal forces?
It would be the resultant.
Right, and what would the resultant of the two be? If I have 10 newtons to the right and 2 newtons to the left, what's the resultant force? 10 to the right, 2 to the left. How do you find the resultant when they're in the opposite direction? You subtract them. So what would the resultant force be? 8 newtons. It would be 10 minus 2, 8 newtons. Well, here we don't have numbers yet, so what's going to be the expression for this net force right here when we have the tension force and the force of friction? Huh?
I don't know.
Well, instead of 10 minus 2,
The difference of
Tension
G
minus
minus
right, right. So it's basically just going to be
the difference.
T
minus F.
minus the force of friction.
Isn't it plus? Because
This would be T minus the force of friction, and since that force of friction is going to the left, it would be a minus because it's going in the opposite direction. You subtract the two.
Okay.
but
Yes?
I was like, if you want just a general equation, like one being T plus S sub F, because the friction could be positive or negative.
Well, usually in that formula,
Because like what
the
if
force of friction is kind of like this symbol right here. Those symbols mean the magnitude, which means like the size. But people don't put those symbols there. but it's kind of like assume that basically this right here is the magnitude, the size.
So it's not. You're not thinking.
So it's kind of like the absolute value of it.
So it's not really a negative force.
So yeah, so we're not gonna, it's not gonna be a negative number. I mean, technically, what you're doing, you could just call it f sub f, and you could say t plus f sub f,
And f sub f would be negative.
and then f sub f would come out negative. That's technically correct too, but that's not as common. Okay, good question.
So if T minus the force of friction equals F net, can we say that T minus the force of friction equals the mass times acceleration?
Exactly. So it would T equals m1, but what was m1? 10 kilograms times the acceleration. But remember, in this problem, there is no force of friction. So in this problem, there is no force of friction. Hey, whoa, man,
Wow.
that was crazy. There is no force of friction, so guess what's going to happen right here? So, basically, what's the net force equal to in this case?
Tension.
Just the tension force. It's just the tension force pulling it to the right. Now you might be saying, Mr. Sosinski, what about these vertical forces? The weight force and the normal force. Guess what their deal is?
Cancel each other out.
They cancel each other out. Hasta la vista, baby. So their resultant force is 0.
Oh wow.
The weight force and the normal force, they're just going to cancel each other out.
Hmm.
Okay? So basically, there's our first equation. But we don't know the tension or the acceleration, but that's our two unknowns right there. But in order to solve for two unknowns, how many equations do you need? Two equations. Guess where we're going to get our other equation?
The other one.
The other mass. We apply F net equals ma to the other mass. So that's our first equation.
So I'm gonna have T equals.
So now F net equals m2 times a.
T equals.
But now remember, we established that the down direction is positive. So we said down is positive. So when you go to do your net force, it's always all the forces in the positive direction minus all the forces in the negative direction. So over here, back to Zach, here we have this object, and we have the tension holding it up, and we have m2g pulling it down. So what's going to be my expression this time for the net force?
The difference between m2g and t.
Exactly. Bravo. And of course, that's going to equal m2a. But we know what m2 is. What was m2?
15.
So it's going to be 15 kilograms times g, which we're just going to round to 10. So easy. Minus t equals 15 kilograms times a.
That's your second equation.
And there's your second equation.
System of equations.
Yes?
What if you make the acceleration become negative for the second one? Because it's going downward.
No.
That's just as viable. That's just as possible, okay? But what I suggest you do is say, hey, I'm going to let down be positive, and then take the forces pulling it that way and subtract the forces going the other way, okay? That way, when you have your two equations written, this A is exactly the same as that A, and this tension is exactly the same as this tension. If you wanted to make down negative, then guess what you would have to do with these two terms right here?
Make them negative.
You would switch them. It would be T minus m2g, because you always take the positive ones minus the negative ones.
Because essentially it's an absolute value.
So,
So you can also use the negative.
right, but I don't suggest you do that. I
But it's
suggest you
different.
say, hey, I'm going to let down be positive.
But
to
wouldn't
the
you
four
get the
forces.
same answer?
Yes.
If you did it from the beginning as down is negative.
Yes. 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 Thomas.
What if the tension
No. Because if those two were equal, that tension up and the weight force down, then it's not going to be accelerating. But we already established in the original problem that it's going to be accelerating. So last but not least, we're running out of time. I want to finish this up here, ladies and gentlemen. Hold on, we can do it. 3. Simultaneously solve the system of equations. Say that 5 times fast.
Simultaneously solve system of equations.
Okay, well, that was fun. Those are the longest resets I think I've ever seen in my entire life.
Can you check them? Can you check number 2? We'll do number 3 tomorrow. Bam.
Okay. And I'm going to quickly do it right now. If you want to watch, if you need to go, hit the road, Jack.
the
So
road,
I
Jack.
rewrite the formulas without units because then it looks so much easier. T equals 10A and 150 minus T equals 15A. And I'm just going to add those formulas together. When I add down, I add the two left-hand sides together, and what would I get?
Could you just substitute the 10A for the T? Yeah,
150 minus 10.
And if I add the two right-hand sides together, what do I get?
25. No, I'm just substituting 10A for T.
And then if I solve for A, what is it going to be?
5A equals 150.
7.
6.
6. And then if I substitute that back into my first formula right here,
60.
60.
Alright,
Oh, we did it!
Yas.